Hi everyone. In today's class, we'll discuss about different types of fins and later we'll have a detailed analysis of long fin.
Now let us discuss about the three different types of fins. One is I already mentioned long fin. The other one is a short fin. So as I already told, it is not only the length. Some other parameters also decides whether it's short, long. Okay. And another type of fin is fin with negligible heat transfer from the end or consider the end as insulated and as insulated. So these are the three different types of fins we are going to discuss. So we will start with the first kind, that is a long fin. Now long fin is one in which the heat flow from the end of the fin is negligible. So heat is flowing from the base of the fin to the end. So heat is conducted from the base to the end. But during this conduction process, from the fin surface, heat is also conducted away. So this conduction process, when the fin is long, as the conduction proceeds, along the length, when the heat is flowing, heat also getting conducted away from the surface. When it comes to the end, there will not be any temperature difference at the end. The temperature considerably decreases. So such kind of fin you can consider as a long fin, where the temperature difference becomes zero. I'll give an example, like ladle or the spoon which you are using for frying something. And so in the kitchen, you use a spoon. There are small handle spoons are there that will easily become hot at the end. But if you use a very long handle for the spoon, at the end, the temperature you can easily hold at the end because the temperature will be almost room temperature. Such kind of that can be considered as a fin. That long spoon or short spoon, whichever it can be considered as a fin. But short spoon is a short fin, very short fin. Okay, it will get heated up at the end, whereas long spoon at the end it will be almost temperature of the surrounding. So in that case, condition at the end is there is no temperature difference or temperature difference T minus TA will become zero. The temperature at the end will become more or less TA. Okay, so the temperature difference becomes zero. So let us see the two boundary conditions which I am going to apply. So to find out the constants of C1 and C2. So first we'll go for the first condition, which is applicable for all the three types of fins which I mentioned. That is at the root of the fin, that is when x is zero. You remember the diagram which we have already seen. X is zero means at the base of the fin, where the surface of the plate from where it is conducted out. So x is zero stands for the surface of the fin, where you will have a maximum temperature. And temperature you can represent by T0. When x is zero, the temperature of the surface will represent by T0. And TA is the ambient temperature. So the difference is theta 0. It should be T0 minus TA. So that is theta 0. Okay. T0 minus TA is theta 0. Now, when x is 0, theta should be theta 0. So, when x is 0, cos x m0, that is cos x 0, is 1. Okay, so that is substituted here. When x is 0, sin x 0 is 0. So, C1 plus 0 is equal to, when x is 0, theta is theta 0. So, we get C1 as theta 0. So that is one constant of this differential equation solution. Okay, so we can substitute C1 as theta 0. So you get theta is equal to theta 0 cos h max plus C2 sin h max. So we solved for one constant. Now C2 we need to find out. So this solution is this constant C1 is equal to theta 0 is common for all the three types of things which I mentioned. because all the types of fins at the base, the temperature difference is theta 0, that is T0 minus T only. So all the three types of fins, these steps are same. You will get C1 as theta 0. So this solution will be holds good for all the three types of fins which I mentioned. So theta is equal to theta 0 cos HMX plus C2 sin HMX. Now we go for the next condition. Next condition I already mentioned that is at the end of the fin. At the end of the fin, the temperature will become for a long fin. We are discussing about the long fin. At the end of the fin, the temperature is TA, and that is ambient temperature. It is becoming ambient temperature. So because it's a long fin, more or less the temperature, the conduction will almost, when the heat is conducted through the fin, most of the heat is conducted from the surface. When it comes to the end, it is temperature has become almost room temperature, and the end part of the fin is not doing much, okay, in dissipating heat. It is almost room temperature. There is no temperature difference, no convection, because most of the heat is already dissipated through the fin, remainder part of the fin. So temperature for a long fin, the temperature at the end is TA, it is ambient temperature. So theta is T minus TA, and T is TA itself. Temperature has become TA, so T minus TA, and temperature is TA, so you get theta as 0. There is no temperature difference. Fin temperature and ambient temperature are same. So the theta is 0. So that is the next condition. When x is equal to L, x is equal to L, T is equal to TA, or theta is equal to 0. You will put that condition in that equation. When x is L, x is substituted as L, corresponding theta value is 0. And now I'll find out C2. C2 is faucet. If you take this to the right hand side, you will get minus. This you take to the right hand side, you will get minus. And C2 will be cos HML by sin HML, and minus theta 0 will be there. So minus theta 0 cot HML. Cos HML by sin HML, you get cot HML. So C2 is going to be minus theta 0 cot HML. And now we substitute C2 in the previous equation, previous slide. C2 value is minus theta 0 cot HML. We'll substitute here. Okay. So it's substituting C2 as minus theta 0 cot HML. You will get the solution. So theta 0 cos HMX minus theta 0 cot HML sin HMX. This is the solution for theta. Now, since the value of cot HML tends to unity means it's just 1, almost it goes to 1 when it is long or infinite. When the length of the fin becomes large, cot HML become 0.9 almost nearer to 1. So the large value you can check with the calculator. When the cot of something like it is huge value will become almost 1. So cot HML is more or less 1 for a long fin. So you can avoid this cot HML, and you can write theta 0 cos HMX minus theta 0 sin HMX. I remove the cot HML because for a long fin, generally cot HML is 1. Okay, or it tends to 1. Now I'll take theta 0 outside. You get theta 0 into cos HMX minus sin HMX. Now cos HMX minus sin HMX, it is e raised to minus mx. This is from mathematics. You know that cos HMX minus sin HMX is e raised to minus mx. So you get theta is equal to theta 0 e raised to minus mx. And theta by theta 0, you can rearrange theta by theta 0 is e raised to minus mx. So this is the equation for long fin, that is temperature difference. Theta stands for temperature difference. So if you are to find out the temperature difference at any point, that is theta. The theta 0 stands for the temperature difference at the root. Suppose the fin is dissipating heat from a surface which is at 200 degrees centigrade, and ambient temperature is 30 degrees centigrade. Your temperature difference is 200 minus 30 at the base of the fin. The temperature difference 200 is the surface temperature, 30 is ambient temperature. So the difference in surface temperature and ambient temperature, 200 minus 30, that is 178, will be theta 0. But when it comes to some other point, and it is some distance from the base of the fin, the temperature of the fin will be less. It cannot be 200. It might be like 180, 170. That temperature depends on the material. So if it's a good thermal conductivity material, even the temperature drop will be less. But less conductivity material, the temperature considerably drops up after a certain distance from the base. So theta will be the temperature difference at a distance x. Okay, at a distance x, the temperature difference is temperature difference at the root into e raised to minus mx, where x is the distance from the base to the point where you are measuring the temperature difference theta. And m, as I told earlier, it is root of hp by KAC. So this is the equation to find out the temperature difference, or you generally you will be written in this form, and you refer the data handbook. You will be getting the things. You take Kodakram data handbook. There you can see the for a long fin the temperature difference will be given in this form. Okay. Now we'll come to the heat transfer. So we need to find out the heat transfer. This gives the temperature difference. So temperature difference, why it is interested? Suppose you need to find out how the temperature varies along the way. But most of the time people are interested how much heat is transmitted through that fin. So you need to find out how much heat is flowing through the fin. And in the absence of fin, how much you would have conducted. So that will show that the effectiveness of the fin. How much, how many times more in the absence of fin. Say suppose 5 watts were flowing from that particular area, and after attaching the fin, if 20 watts is flowing, so that shows 4 times greater heat transfer. So always we need to find out how much heat is flowing out of through this fin. So that is generally people are interested. So we need to find out the heat flow through the fin. So heat flow through the fin. How do you find out the heat flow? You can use a Fourier law of heat conduction. But suppose you take the middle of the fin, and if you find out the heat conducted. So that heat conducted will be differ from the heat conducted at the base.
Hence, we have to calculate the heat conducted at the base to get the total heat flow through the fin. So Q is equal to minus KAC d theta by dx at x is equal to 0. Differentiating theta equation, we will get minus KAC into theta 0 m sin hmx minus theta 0 m cos hmx at x is equal to 0. So when x is equal to 0, sin h0 is 0 and cos h0 is 1. So finally we get KAC theta 0 m. This expression gives the heat transfer through a long fin.